Hello and welcome again to my Physics Online video lecture series. In today's video, what we're going to be doing is basically like a long example of asymmetric projectile motion. This isn't really any new lecture material in the sense that I'm not going to introduce any new equations or anything. I just thought that it might be useful to work out a longer example using projectile motion but with an asymmetric system. Let's begin by recalling a couple of things. First, what is asymmetric motion? So asymmetric motion or asymmetric projectile motion specifically means that the projectile is not going to start and end at the same height above the ground. So basically what this means is you should not be using the range equation if you're being asked to find something like how far away does it land or how far has it traveled horizontally. The second thing to recall, I guess, is the set of equations which you would need to use for the projectile motion. So this set of equations is basically the ones that say delta x should look like v initial in x times time, and delta y is equal, or maybe I should just use the exact y equation. Y is equal to 1/2 g t squared, negative of course, plus v initial y t plus y initial. So the other equations, of course, are how to split up to get the initial x and the initial y from the initial velocity. So you basically are just using cosine and sine of whatever your initial angle are to get those two terms. So now let's go ahead and do an example. And that's the main purpose of this video, really, is just this example. So I have here a fairly long wall of text example. Basically, you've got a man standing on a cliff. He knows the height of the cliff because he's dropped a stone from it and timed it. Now he's tossing the stone off the cliff. It leaves with a known initial velocity, that is speed, and then also the direction. And we want to know how far away from the base of the cliff this lands. For what it's worth, you might be looking at this and saying, okay, 65 meters high by dropping a stone and timing it as it fell. You may be wondering, how long should that take if we neglect air resistance? For what it's worth, this time would be about 3.64 seconds. I'm going to put that there. You could go work as a separate example that if you'd like. It's actually there as a double check for this example. What I really wanted to do, though, this is T for dropping. What I really wanted to do is label these terms as what they are. So this is the theta. This is your V initial. This right here would actually represent Y initial in the equations. And this how far from the base of the cliff is basically a delta x. What is Y final? Well, it's landing on the ground below, so we could say delta x at y equals 0 meters. Okay. It's also maybe worth noting that before solving the problem, you should draw some sort of a diagram here. So I've got this man standing on top of the cliff. He has tossed a rock with some initial speed. It lands at the base of the cliff some distance delta x away. So this right here is your delta x that you're trying to solve for. This down here is y equals 0. This location here is y initial equals 65 meters. And we also have an initial velocity. I'm going to actually draw it in a different color here. So this is your initial speed, and this is your initial angle that this thing has been projected in. So now we're ready to actually solve the problem. How do we go about solving a problem like this? Well, you kind of have to do it piecewise. So let's kind of write out some steps. So step 1 might be get everything into equations. So get equations set up. So I will say set up. What that basically means is we want to get VIX and VIY, and we want to be able to use these two equations. So this is need VIX and VIY. Okay, step number 2, once you've done that, is use Y equation to get time. So we are basically solving for the time of flight. So you could say to get time or time of flight, whatever you want. There's a few ways that you can go about doing that. I'm going to do the most direct. And then step 3 is to use the time of flight that we just found in step 2. So use time from step 2 to get delta x. And that's basically your answer. So let's walk through these piece by piece. Okay, first of all, I need to get VIX, which was VI times cosine theta. And so that is 16 meters per second. That was our speed times the angle. So 16 meters per second, 25 degrees. Put that into your calculator, 14.50. You also need to get VIY, which is VI times sine of theta. So again, that's 16 meters per second times the sine of 25 degrees, which about 6.762 meters per second. If you're wondering about the underlining thing, I'm just kind of underlining the digits that are not going to be retained as significant figures at the end of this calculation, by the way. All right, we're ready to do step 2. Step 2 is actually kind of the long step of this one. Step 2 says use this equation. Y is negative 1/2 gt squared plus v initial y times time plus y initial. And what I'm going to do is actually rearrange the equation so that I have essentially a delta y plus or minus, as the case may be, a VIYT plus a 1/2 gt squared term equals 0. So basically what I'm doing is I am adding to both sides this term, subtracting from both sides this term, and subtracting from both sides this last term. And so y minus delta y, or y minus y initial is delta y. So this right here is your y minus y initial term. Again, we're trying to solve this equation for time. And you'll notice that this is a quadratic formula in terms of time. In other words, if I rearrange from t squared term to t to the first power to t to the 0th power, I have a 1/2 g t squared minus a VIYT plus a delta y equals 0. And if I pay attention, this is like an a times x squared plus b times x plus c term. So the thing that I'm trying to solve for, the time, should look like negative b, so that's VIY, plus or minus square root of b squared, so again VIY squared, minus 4 times a, which is 1/2 g, times c, so that's your delta y, all divided by 2 times 1/2 g. Right, so now what we need to do is basically plug numbers in and solve. So using the numbers that we had here, VIY is 6.762 meters per second. And this was a negative VIY, so this actually ends up being positive 6.672 meters per second, plus or minus the square root of negative 6.672 meters per second, which we're going to square, so that minus sign goes away, minus 4 times 1/2 g. And notice when I set up this equation, I already labeled this term as negative 1/2 g. So this 1/2 g, these are all positive numbers. So this ends up being 1/2 times 9.8 meters per second squared. And then my delta y, you'll notice that the delta y term is positive here, but I started at 65 and ended at 0. So my delta y is actually 0 minus 65, final minus initial. I'm lower at the end than I started. So this term actually is negative 65 meters. And then all of that is going to be divided by 2 times your 1/2 times g. And again, because of the way that I've set this problem up, my 1/2 times g, these are all positive numbers, and I can, maybe cancel the 2 and the 1/2. Now, what this is going to do, I'm going to need to maybe plug stuff into the calculator. I'm going to get 2 solutions. Eyeballing this, I see that I have a minus sign here and I have a minus sign here. So I can kind of cancel them and turn it into a plus sign. This whole term, since I'm squaring it, this part right here becomes also positive. So I'm taking the square root of a plus number plus a plus number. That means that I'm going to end up with a real answer, which is good. We need that. And also, this term right here is this term here. So when I square it and then add something to it and take the square root, I end up with a number that is on its own larger than this first term. So that means that I'm actually going to get, when I add and when I subtract, I'm going to get one positive answer and one negative answer. Physically, that means that I know which of the two I need. I actually need the positive value of time. The negative value of time would kind of correspond to if I continued this trajectory back over here. At what time would it have had to have been shot from the ground such that it passes through this point and also arrives here? And we've just set this point as time 0, so this would be some negative time. So physically, this part didn't happen. This part did. We need a positive value for the time. So plugging in the numbers, what do we get? So here I actually like to just get everything under the square root and figure out what it comes to after I've taken the square root and then add and subtract. So the positive root ends up being plus 4.3867, but let's not retain more digits than that. There's also, of course, the negative. Again, though, we actually only want the positive root. Okay, we're ready for the last step, or kind of almost ready. Quick double check. This number should be larger than the time that we found from just dropping the stone, which is part of why I gave you that time. Notice that that time was 3.64. This time is 4.38. So this time is bigger, so our kind of gut double check is working. So step 3, we now can solve for delta x. It should be v initial x times time. The v initial x we found as 14.5 meters per second. And then the time we found up here as 4.387 seconds. So we multiply those two together to about 63.61 meters. Now again, 2 sig figs, that means delta x is about 64 meters, and that's a wrap. Thanks for watching.